test.
He's like,
So I'm giving you guys this a little early.
We're getting our testes, guys.
yeah, it's like that. I've been getting yelled at.
This is so good.
What? Are you serious?
You all failed
Hey,
I'm sitting there like,
since you guys have the quiz tomorrow, I'm giving you the review early.
When there's only 2 urinals.
It's not due tomorrow, but if you want to use it to help study for your quiz, you absolutely can.
Just gonna ask you an extra practice.
just gonna-
Yeah, he's
As a warning, I'll do it at home on my whiteboard, but if I bring all these answers in, then I'll have to, like,
Then I'll get couch paper.
I can read it.
That's so against the
Do it now.
Still using the system.
Just don't think I'm
I don't want to do it now, 'cause we're doing
I told my
it
parents, I was like, as a joke.
Don't think
Yeah,
about
I was like, fine. I know the first one.
it. Yeah.
Track your child.
Just kidding.
So I have.
It's repel and attract.
Didn't
You stink at this. You stink at this.
You're so bad. Oh my word. That's so embarrassing.
Ready?
I'm ready.
We are going to draw electric field lines.
I feel like I should have known.
Keep going, Kramer. Turn your book to some page near 507.
Frames.
Section 3. Right there. What page is that? Go back. What page is that?
507?
Yeah, turn there.
That's not even near.
567, everybody get there. Now, your book is actually kind of a nasty looking.
Ew.
Oh, like
That is like something Cole left in it.
Gross. Is that magnetic lights?
Why is Creeper's eyes?
Mine looks better, actually.
Magnetic
Wow.
lights.
So what essentially they did is they took 2 charged objects, they put them close to each other, and they put like a bunch of like metal shavings, and those metal shavings align themselves with the imaginary electric field lines. Well, you can't see them.
Oh, that's not that real.
Okay. I don't know if you guys can see mine. Mine, I think yours is like a colored version of mine. But everybody see mine?
Yeah.
Do you not see?
Are you
Mine? Yours actually doesn't look that awful. If you look at the visual to the left of yours, it kind of shows you what it would look like a little bit nicer. And then you can see, you're probably wondering, well, why on the last one, why is there like some brown stuff in between if it repels? Well, that's probably because some of they got stuck there.
Once they're all getting pushed upon, so they
Yeah, they're in equilibrium. Alright? So what we are going to do is draw electric field lines that if we were to see this in practicality, what it would look like. So there's a few rules here. First rule. Okay? And again, it's like sign convention. Could they have done it a little bit differently? Sure. Okay? They say that lines must begin on positive charges, okay, or at infinity, and must terminate on a negative charge, or at infinity. So what I mean by that, if I'm just doing a
Terminate at it.
positive charge, okay, first off, if it's a positive charge, it's going to the electric field lines are going to start at the positive charge, and they're going to end at infinity. If I just have one, obviously, if I have more than one, we'll get to what that looks like. Okay, so this is what it means if it says either it begins at the positive. You're probably thinking, well, where would it ever begin at infinity? Well, can it ever begin at a negative?
No.
No, cannot begin at a negative. So where's it going to begin if you have a negative? At infinity.
Is this only with positive charges?
Why can't it? Well, it probably could, but this is what they chose to because it can't be both, right? Otherwise you'd be confused on how to do electric field lines. So they said, this is the standard, we're saying it either begins at the positive or at infinity. It either ends at a negative or at infinity. Well, this began at the positive, where did it end? Infinity. This began at infinity, ended at a negative. So, can it end at a negative or at infinity? Did this end at a negative?
Yes.
Did this end at infinity?
Yes.
Okay. Then it says it can either begin at a positive or at infinity. Where did it begin?
Positive.
Where did it begin?
Infinity.
All right. Does that match?
Yes.
Does this go under isolated positive and negative?
Yes.
I would.
Yep.
Does this align with like actual physics, or is this just like, hey, let's just say something so that we can make it easy on?
I'm trying to comprehend exactly what you're asking.
Like,
Because are you when you put like bits of metallic things in between things that have charge, you're not going to see an arrow. You're just going to see a line. Does that make sense? So like they don't.
So the line is just them trying to simplify the whole idea.
Yeah. Because you're not going to see an actual arrow, right? But usually when we do lines, we do arrows. Also, I think another reason why they say that you always end at a negative is because the negatives are the things that move. So I don't know for sure. That would just be my guess.
So do I have to write anything else underneath isolated positive random charge?
Nope.
It's just those.
Okay? And then it says we have one positive and we have one negative, right? Isn't that what your next little blank is? Don't you have a next little blank that says one positive and one negative with the same magnitude? Okay? Here's where the magnitude comes in. The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to its charge. So if these have the same charge, they're going to have the same number of lines.
So one line.
Okay? Now, remember, where do the lines always start? Positive. So if I started right here, where would it end?
At the negative.
Oh, no, no.
Because that's the arrow too.
That's one field line. Now, you could be creative and you could put 100 field lines on here. Or you could be boring and put 2. Okay? I like to do somewhere in between. So if I start here, it's going to always go out perpendicular to the charge. So if I start here, it's going to attract and bend and end there.
But one is legal. One's not legal.
No, I want at least 3.
Wait, so it's,
All right,
does it
that's
have
really
to be
boring.
even number?
Yes.
Then why is it three?
No, I mean, I have to have the same number of, if they have the same magnitude, I have to have the same number of beginnings as endings. And I'll show you an example when they don't have the same magnitude.
So in this case, only half the lines are originating from the
Does
charge.
rule 1 go with isolated and rule 2 goes?
All these rules go with everything.
It looks like Clippy from Microsoft.
Stop.
Okay,
Okay? Does rule 1 apply here?
yes.
Did I start at the positive?
Yes.
Did I end at the negative?
Uh-huh.
Yeah.
That's right.
Okay? Now, I could do one right here. Should I have it kind of coming off this way?
Yep.
Oh boy.
These look like
The
those
face,
things.
don't change it. No, he's gonna.
Oh, no, it's like a.
Ew, that's
That's what I thought too.
Now, if you were to come straight this way, I would probably then go like this.
Because the world's a circle.
Whoa.
I'm not even going to completely bring it all the way around.
That's because the world.
But the reason why, guys, it would not be okay to put this line, but not have this line. Because that would tell me that this has a stronger charge than this does. because the number of lines determine the magnitude of the charge. And so if they have the same magnitude, they have to have the same number of lines connected to them. Does that make sense?
Does it always be an odd number of lines?
No, it can be however many number of lines you want.
Some might say blurs.
That's why I said you can be boring and put 3 lines, or you could be a little crazy and put 1,000 lines.
5.
It's a safe
The
medium.
number of lines determines the magnitude.
Oh, hey, look, it's this.
I forgot what you said.
Now, do I know what, I'm just saying that I don't actually know what the number here is,
Based on which one's stronger.
but I know that they both have the same magnitude, that's why they have the same line. If I have something that's twice the magnitude, it better have twice the lines as the other guy.
Oh, my lands are
Okay.
close.
And then number 3 just says no field lines can cross another. Okay, that they should never intersect each other or cross. Okay? Well, let's do 2 charges that are alike.
Well, the magnetic field and electric field is very similar in
Wait,
You
what do
can
you
make magnets that have certain.
So I think I have 2 positive or 2 negative.
Like a field that looks a certain way.
Well, let's just say we have 2 positive guys. What's the matter?
Oh, yeah, I don't know. What is tangent to the electric field vector?
Where are you seeing that?
Second
Way
bullet
at the
point.
top.
Electric
Before
field
that.
lines are tangent to the electrical field vector.
We have 2 bullet points for the fields.
The number of electric fields.
It just means, like, what's that word I'm thinking of?
Perpendicular.
Perpendicular to it, yeah.
Parallel.
Perpendicular.
perpendicular? Because T is the electric field.
Yeah, as you sort of the charge.
Yeah.
What's it?
So perpendicular?
What's wrong?
The lines that come off the charge.
You can't draw a line like on the edge
I'm
going
not
straight
gonna go
down.
like this.
What is
Watch.
perpendicular to a circle though?
Oh, it's just, oh.
Yeah, I got perpendicular to the circle. Like this would not be perpendicular to the circle.
Correct. But how would the one where you did the curves be perpendicular?
How it comes out perpendicular and then curves after. Okay? So now, these are positives. It would be the same idea, but a little different if they were both negatives. And I'll kind of talk about that in a sec. So if they're positives, they originate from the positive, correct?
Correct.
So if I had one coming out perpendicular from here, what are the 2 positive things going to do to each other?
Oh, go away.
The book didn't do it that drastically.
It's like, you know,
As long as like we have the main idea of this. Are
And you don't need 1,000 lines, but if you have different number of lines, that tells me they're not the same magnitude.
so what you're saying is write as many lines as possible and then you just won't count.
No.
So,
Well, you still
Opposite
count
side.
them no matter what.
what happens if they're not the same magnitude? Like
I
what
will show
happens
you in a
if-
second.
This one's the
If
bottom.
you continue to go down, I will give you an
The
example of
picture's
that.
bottom.
James, you're a cool guy.
This one?
No, the bottom of the book page.
Are these not spiders?
Cole, you're a spider.
Oh, that is a spider, I hate you.
Spider-Man.
Spider.
Cole is
Okay?
spider.
Do I have it starting at the positive and going to infinity?
Amen, Chris.
Why is it not ending on something else?
Because there's
Because
no
nothing ends
There's
at
no negative. We know it either ends at a negative or at infinity. If there's no negative, it'll end at infinity. Okay? Do I have the same number of lines for each of these?
Amen, Chris.
Which means that the magnitude of these 2 charges are equal. I don't know if it's 2 plus and 2 plus, or if it's 12 plus and 12 plus. All I know at this point is that the magnitude is the same. Now, we could have made a rule that said, you know, somebody with a higher magnitude has more lines. But we're not going to make that rule. Now, if these were negatives, they're both negatives, are they still going to repel?
Yep.
What is the only difference going to be?
We're gonna have the arrows.
Arrows.
Like, is he actually gonna come all these lines?
You don't have to put this in, you just need to know it. I'm just showing you that it would just look like this.
My friend's pointing at us.
Think I'm right. Could you call so like this?
You need to not do that.
Rice crab.
Look at this man.
What do you do?
Doesn't this look like a muscle?
Wow.
Okay,
Flex.
now, let's do one where we have opposite charges
And different
and
magnitudes.
different magnitudes.
Because opposites
Wow.
attract.
So let's say I have a 2 plus and a 1 minus. Okay? If I have a charge that is twice the magnitude of the other, it must have twice the field lines.
And just watch me.
So 1,
I just gotta make it bigger.
2, 3, 4, 5. So if this has 5, this needs
5 more.
10.
Are the ones coming off the counting as
Yes,
the first
you
5?
need double.
Okay.
Wait, Kramer, why is the one with more going towards the other one? If it has more?
Always starts with the positive, ends with the negative.
Oh, really?
What you say is because it's 2 plus and negative twice.
So if this has twice the magnitude as this, this will have twice the electric field lines.
Yeah.
So if I have 5 ending here, I need to have 10 starting here. So the ones that don't, so you're probably thinking, well, I have 5 that start here, but where do they end? Well, they have to end at infinity then. Yes.
So there's one line. Never mind. So the lines are just, they just have to be proportional. There's no like 2 lines equals this many charges.
That's, yeah, so that's what I was saying earlier, was that we could have a rule that's obviously the stronger the charge, technically the more field lines you should have. But then would a 2 mean 2? Would a 3 charge mean 3 lines? You see what I'm saying? So yeah, but in theory, if you had a charge that was greater, it should have more lines.
So this one has 10 of them, and then
Yes.
5 of them.
When drawing your infinity
This has 5, this has
positive, do you
Amen,
want us to
girl.
curve it
Amen,
towards
girl,
negative?
friend.
Yeah, it's still gonna curve towards a negative, but yeah. But it won't come back to the negative.
Did you know my
Okay? Any questions on this? Here's the rules you should remember. I didn't show you every example. If this was a 3 plus, I would need 3 times the lines leaving it. Okay? If this was a 2 plus and a plus, same idea, just they would all be terminating at infinity. Okay? If I change this to a plus,
Oh my land. It all terminate at infinity. So
Can you
there's-
believe that?
That one still will have one.
Bryce, you're gonna terminate at infinity, meaning you're gonna
But then the
terminate.
one at the end, he forgot.
We're all gonna die.
they repel, right?
Unless you're a crocodile.
So they go
I had a curve in the
Are
other
we talking about
way.
habitable infinity or?
What is that? There's no, what are you talking about?
Have you never
Okay.
seen the hotel? What's it called?
Transylvania.
So we'll say,
For sleeping.
so I'll just do
All that area.
Oh, great.
I got what, 8? So I need how many from here?
4.
Ah, I see. Exhibit line.
I don't like the spider bullets.
So still just twice the magnitude.
Still twice the magnitude, it's just now we're repelling instead of attracting. So we never have anything terminating at a negative because there isn't any
This one
negative.
is just a guy with his hands up, running.
He's like, ah!
Friends, I am learning.
He's one of those guys.
actually have to have 8, while this one has 4, while this one doesn't, like this, they share this one.
Because the reason why they share is because one's positive, one's negative. So there's an attraction.
His arrows are like towards each other.
These don't attract towards each other, so they repel away.
This is only 10 lines, but it's actually equally 50.
No, that is his face. No, you made it worse. Get rid of it.
It's like Mike McGill.
Mike was out.
Oh, wait, no, cool. I thought it was a spider.
Yeah, to me that doesn't seem weird. I'm not sure why.
What is that?
He's gonna stop the spider. He's like,
$5.
You added 4 lines. Add 1 more to the
This is
right.
like 5
No,
lines.
it's a little mouth thing.
I understand.
Alright, he's gonna plug the spider then.
Camera back.
Actually, it was Samwise Gamgee.
I actually prefer this.
Spider,
really?
Spider.
Yeah, I was about to kick you yesterday.
Yeah, same. Actually, I
Say the line.
So much self-pity, I wanted to freak out.
wow.
Two-thirds sometimes, sorry. Alright,
Don't worry, I'll be happy to go.
Is there a sharp side?
no, I mean, you can have bad days.
Balls are black.
Last thing here.
I think to like switch things. Fight them all to the same level.
Like, you know, like ball for trauma, like a baseball bat, there's no sharp edge to a ball, so if you kill someone with a ball,
Balls up.
Bludgeoning drama.
Not even necessary, like no one needs to know that.
Alright, so, I'm gonna stay in the same area because there is a short section reading on this. And this is actually kind of difficult, even pretty difficult for me to kind of explain.
So like your hair.
So I don't know, it's like the last page of your section 3. Somebody find that? What page that is?
It's page 568.
568. It should say conductors and electrostatic
Yes.
equilibrium.
Yeah, boy.
Okay? So this is more making some inferences based on what we know about equilibrium. Okay? What do we know about equilibrium?
Zero net force.
Okay, so zero net force. So this is saying if we're at equilibrium, we have zero net force. These are some things that we can deduce from this. Okay? The very first thing, if you have zero net force, the electric field is 0 everywhere inside the conductor. Why can we make that rationalization?
Because there's no outside.
Because it's not going everywhere.
It's
It's all equal.
Think about it. Remember we said equilibrium was what?
Zero net force.
Zero net force.
Well, it's
So
not
if we have
moving.
zero net force,
It's not moving.
we can assume that there's no electric field inside the conductor, because if there was an electric field inside the conductor, wouldn't that cause the electrons in that conductor to move?
Oh my word. But don't they do move it? Like
Not if it's an electrostatic equilibrium. Yes,
Oh.
but if they're at equilibrium, there's no force, so there's no movement.
Why is there no net force?
So you just got a conductor.
It's not asking why there is no net force, it's just saying if you're at equilibrium, you know you have no net force. There's a variety of reasons for why it could be at equilibrium.
So is that just like having the copper bar?
Yeah, that has allowed all the electrons to disperse equally so that you do not have any net force. Now, could I take a charged object and charge that conductor? Absolutely. But let's just assume this was some object that had allowed the electrons to move so that there was no forces acting on each other. Equilibrium. If there's no forces acting on each other inside the conductor, would we have any electric field inside the conductor? If we had an electric field inside the conductor, the charges would move, and we know that movement can only happen due to a what?
Acceleration.
Force.
We're still stuck on these.
Does that make sense? If something's moving, the only way it's moving is if it is acted on by a force. Okay? Second thing. Any excess charge on an isolated conductor resides entirely on the conductor's outer surface. Why?
Because it gets like,
There's
pushed
nowhere
down
else
to
to
the outside.
go.
I mean, it's going to try to get as far away from each other as possible. And what's the farthest way you can get away from each other is get to the outside. If they all sat in the middle, they'd be right next to each other, right?
Yes.
So in order to get as far away from each other, they're going to typically reside on the outside. Does that make sense?
Yeah.
Okay. Next one. The electric field just outside a conductor is perpendicular to the conductor's surface. This is what I was saying earlier when we were doing electric field lines. Let's say this is a conductor with some positives and some negatives and whatnot. Okay? It's saying that the electric field lines is perfectly perpendicular to the conductor.
Is that only in equilibrium or always?
Guess I don't know what it would be. I would assume it would be that always. But it would definitely have to be that at equilibrium, because if this was not perpendicular, what you would have was you would have a force that would cause these guys to start moving in there. Yes?
Kramer, this is
No question, stupid.
the circle, what is that? That's not a particle,
Imagine that. Obviously, I can't draw a three-dimensional shape
so that's
on.
like the tube, or the,
A good way to say that would be like a metal sphere.
a metal sphere that has a bunch of atoms in
Everything has atoms in it.
it. So what are those?
I'm just saying that I have a metal object that I have charged. It has charges in it because of atoms. Yes.
And God created set atoms.
What?
So God created set atoms.
Okay. Now I'm gonna read what the book says on this one.
Do it, it's a trap.
Wait,
All right. We can understand. Listen. We can understand why the electric field just outside a conductor must be perpendicular to the conductor's surface by considering what would happen if it were not true. If the electric field were not perpendicular to the surface, the field would have a component along the surface. This would cause the free negative charges within the conductor to move. And if they are moving, they have to have a what on them?
Force.
And we said that that force is what?
Acceleration.
Zero.
Not even.
Zero.
Zero. So what it's saying is,
Hence.
we know that a force perpendicular to an object isn't going to cause an object to do work. Do you guys remember that?
Yeah.
Okay? So if it comes out perpendicular, no work is going to be done. But if it doesn't come out perpendicular, you would have a component that would be along the axis of the spherical object, causing a force to be created. It would cause the objects to move, and if they would move, they have a force, and we could no longer be at equilibrium then. So what they're saying is, the only way for us to be at equilibrium is if they were perpendicular. Because if they weren't perpendicular, we know we wouldn't be at equilibrium.
Oh, there's no work, it's not moving around.
So what's zero on each side? It's just because,
Zero on the inside.
or it's equilibrium inside the
The first one?
conductor. Yeah. What was that thing again?
Birch.
Because if there was an electric field inside the conductor, that would cause the particles inside the conductor to move.
I didn't know
But I know if I put a charged particle outside this, it's going to be in the field and it's going to move. Does that make sense?
I didn't know which direction to draw the arrow to slant like that.
You won't have to do that. I don't even know.
Well, it's positive. It was a positive charge.
Yeah, that would be my best guess. I'd have to look that up. I don't know that off the top of my head. Is there probably something? But I don't really care. Okay. Now, last one. This is a little bit difficult. It says, on an irregular shaped conductor, charges tend to accumulate where the radius of curvature on the surface is smallest. So they have an example or a visual in your book that kind of looks like, that's not that good. still not that great.
The heat rise.
Alright, I can't seem to draw this picture very well.
The pear? Pear?
No, have you not seen that garlic?
Draw a pear.
What did you say?
Have you not seen that garlic?
Everything is
Is that an
apple is
electric-
pear.
No, what's it gonna say?
Whoa.
Nice one.
That's a pizza slice. That is Mr. Analysis nose.
Draw the nostrils.
So that's good.
Yes!
There they are.
Why would they have that?
It's a
at the end
duckbill
of
as seen from above.
What is going on in here?
Alright.
It does.
So this one can be a little bit tricky to explain. It says, let me read it here. It says, to see why charges tend to accumulate at sharp points, consider a conductor that is flat on one end and relatively pointed at the other. So I'm assuming this is the flat end and that's the pointed end. Okay?
Wow.
Any excess charge placed on an object moves to its surface. Okay? In the figure, which is what I have, well, I don't have this.
The longer arrows are on the pointed side.
It was supposed to sound like a beeping fire alarm.
Yes, I thought it was fire.
Okay. This figure shows the forces between two charges at each end of such an object. At the flatter end, these forces are predominantly directed parallel to the surface. Do you see how this force arrow is pretty parallel to the surface? Okay? You see how these arrows for the most part are more perpendicular to the surface.
Yes.
The way you draw it is a lot different than the way the book does it, honestly.
Is a lot more clear than the book? Okay, good. Now, at the flat end, these forces are prominently directed parallel. Thus, the charges move apart until the repulsive forces from other nearby charges create a state of equilibrium. At the sharp end, however, the forces of repulsion between two charges are directed predominantly perpendicular. And when we said there's a perpendicular force, does that cause the object to move? No. So what ends up happening is charges will actually accumulate at the sharp points because there will be no force causing them to move. But when they accumulate over here, because the force is parallel, it will cause them to separate. So the reason why they tend to migrate towards the sharp spot is because the forces are perpendicular and cancel each other out or don't do work. But on the flatter side, they are more parallel, which means the forces are actually going to cause them to move and migrate away from each other.
So they don't want to move.
What was that?
They don't want to move.
I mean, ideally, to get to equilibrium, yes. Yep, remember we're talking equilibrium. So what they're saying is, these charges will move until they reach equilibrium. These are already at equilibrium because of perpendicular field lines. Or forces. Parallel to the surface. Here's the surface. A little bit. A little bit.
That's a degree.
Yeah, what makes it look like it's basically the same thing?
Yeah. All right, we're done.